Okay, thanks a lot for the introduction. And I'm going to talk about the blockchain and cryptocurrencies, including the good, the evil, and life, and the universe, and to cryptographers in this room, the composable universe, and everything. So this will cover a couple recent and ongoing works joined with my students Ahmed Kosba, Andrew Miller, Zikai Wen, and with my colleagues Ari Juice and Babis Papamento. Okay. Here's the plan. I'm going to first introduce what is the blockchain model of secure computation, and I will try to explain it in a cryptographer's language. And then later in the talk, I'll talk about how to design protocols in this blockchain model of secure computation. There has been a long line of research on cryptographic currency, and in this talk, I'm going to specifically focus on decentralized cryptocurrency, and the first popular embodiment of a decentralized cryptocurrency, as we all know, is Bitcoin. Okay, and this also popularized the concept of a blockchain. And what is a blockchain? In layman's terms, in Bitcoin, as we all know, there's the mining process. There's a network of distributed miners, and the miners solve computational puzzles. And as a result, they reach consensus about the end state of the global ledger. And roughly speaking, every 10 minutes, a new block will be mined, which includes new transactions that have entered the system. Okay. This talk is not going to be about Bitcoin specifics, but rather, I'd like you to think of the blockchain in a conceptual manner. So conceptually, what is the blockchain? The blockchain, as we all know, stores data. And in the case of Bitcoin, the data is essentially a global ledger. And the blockchain performs computation. And in the case of Bitcoin, this computation is transaction verification. Okay. And as we all know, both the data and the computation are decentralized. And essentially, the network is reaching consensus about both the data and the computation. And also, the computation will determine the most up-to-date state of the data. In the most recent Eurocrypt, Gouret and others showed the security of the Bitcoin backbone protocol under the assumption that the majority of hash power in the system behave honestly. Okay, so specifically they show that the protocol will reach consensus, and moreover some liveness property will be satisfied. And actually Agilos will be giving a talk on Wednesday about this subject. So therefore this talk will not focus on the secure consensus protocol design, but rather as a starting point, I will assume that a secure consensus protocol exists. And let's think about, what we can do with such a secure blockchain. Okay. So when we think about the consensus protocol, of course, we need to think of the Bitcoin network as being distributed. But when we actually use the blockchain to design protocols, it will be better if we think of the blockchain as a single conceptual entity. And specifically, here's an important observation. This blockchain entity can be trusted for correctness, but it cannot be trusted for privacy. Correctness because, when the network of peers reach consensus, they will agree on the correct result of the computation. But as for privacy, as we all know, everything that you store on the blockchain is exposed to the public. Okay, and let me reinterpret the statement using universal composable terminology. Okay, and the way to think of a blockchain is to think of it as a cryptographic functionality. So in the UC model, we have parties and we have functionalities. And here we can think of F blockchain as being a functionality, but in comparison with ideal functionalities in the MPC literature, as we know, like a standard MPC, ideal functionalities will preserve both privacy and correctness. But here, this functionality actually will expose all of its internal states to everyone. Okay, any questions? So therefore, when we talk about the blockchain model of secure computation, we are effectively designing protocols in the F-blockchain hybrid world. Let me give you a concrete example. So here's a way to think of Bitcoin. Okay, I claim this is not very precise, as I will mention later, but one way to think about Bitcoin is that it realizes Bitcoin functionality that's essentially a global ledger. And when parties send a transfer command to the functionality will, in this case, the sender is S and the recipient is R. The functionality, of course, notifies the adversary of the event, and then it will check if S has indeed has this amount of money in its balance, and if so, it will make the transfer by updating this global ledger. So in reality, Bitcoin actually doesn't implement this ideal functionality. This is like an overlay simplified version. But for the purpose of this talk, it helps to think of Bitcoin in this simplified manner. Okay. So given this, as we can see, this is a very simple blockchain functionality. And the obvious question is, what else can we do with the blockchain functionality? So let's liberate ourselves and think about what more things we can do. Okay. And with this, I'm going to mention that, so Ethereum is going to be a new cryptocurrency that will be launched soon. And the main idea behind Ethereum is to support what's called programmable smart contracts. So now many of you may have heard of Ethereum and heard of programmable smart contracts. Okay, and I've also been asked to explain smart contracts to various people. And here's a way to kind of explain it to cryptographers. So the layman's way to explain smart contracts and Ethereum is that Ethereum effectively offers a Turing-complete language on top of something like Bitcoin. So as we all know, Bitcoin doesn't have a Turing-complete scripting language. But in a cryptographer's terminology, essentially we can think of Ethereum as offering this functionality. We still have a ledger, like in the case of Bitcoin, but Ethereum is also parameterized by a set of user-defined contracts. And these contracts can, they are kind of standard Turing machines. They have memory, they can do computation, and these contracts can basically talk to this global ledger. And also, like I said, this functionality would expose all of its internal states to any party that queries the functionality. Yes?
Do the smart contracts have access to external sources of information, like
you can,
the price of a stock on the stock market or things like that?
Yes, you can think of, so this contract can receive input from any party, including, let's say, a stock exchange can provide inputs to the contract as well. So basically, the stock exchange can be a party in your system as well.
And there's a way to make sure that everybody agrees what the price was on a given day and things like that.
So for instance, if your contract depends on the stock price, then one way is you can hard code the public key of the stock exchange in your smart contract program. And if I'm interacting with the contract, it's implicit consent that I agree to the programmable logic of this contract, including agreeing on who should be the party that has the say on the stock price. Yes.
You will give an example?
Yes, I will give an example later. Yes.
Do these contracts then have persistent storage outside of the global ledger?
The contracts, the storage are instantiated on the network of miners. So every miner will store the state corresponding to the contracts. But the protocol itself, the participants can have local storage, right? It's kind of like I said, the protocols in this model are basically protocols in this Ethereum hybrid world. So every party in the protocol can have its own local storage that's not part of the storage of the contract. The contract is basically this ideal functionality, and this functionality storage is basically stored by every miner in the system.
So the contract, there's no consensus on the storage for the contracts?
The network of miners will reach consensus on the state of this functionality. So all the states will be have consensus.
Including the storage for the contracts.
Including, yes, including the storage here. Yeah, if you think of this as a program, these are just like functions or modules in the program. So this big program has storage corresponding to the program.
Is part of the consensus? Yes or not? So you're saying it is?
Yes, it is. Like basically the consensus is for this whole functionality.
Including the code.
Yes, basically what happens is in every epoch, the miners will run this big functionality, including all the user-defined contracts in the system, and update the global state. And you can think of the state as being partitioned across these contracts, so every contract has its own state. But for instance, all these contracts will share a global ledger.
An example would be good. An example would be good.
Okay. Okay, before I give an example, Ethereum is going to launch very soon, and in fact, there have been several planned pre-releases that are going on right now. Okay. So there are a lot of details that have been hiding. I talked about this global ledger, but for instance, I haven't talked about time, I haven't talked about pseudonymity, and I haven't talked about how to model front-running attacks. Time is very important because if you think about the blockchain, it advances in block intervals, so there's a natural notion of time. And it turns out time is important for designing protocols with financial fairness in the system, because if parties abort, the aborts can be made evident by timeouts, and then you can financially penalize the parties that abort in the system. Okay. Pseudonymity is also important because in this framework, every party can make up an arbitrary number of public keys or pseudonyms, and then they can basically act based on these pseudonyms, and these pseudonyms cannot be linked to their real identities. And in the standard UC model, like there isn't this notion of pseudonymity, so you have to explicitly model that in your framework. Okay, so in our work, basically we think it will be helpful to have like a UC-like model for the blockchain model of secure computation, and our approach is to basically use a wrapper-based system where we model these things explicitly in the wrapper. So when you write your user-defined portion of the functionality, you don't have to worry about these common elements. So this notational system is designed to be kind of user-friendly by factoring out these common and often tedious modeling facts. Okay. I wanted to quickly mention some earlier works that effectively were designing protocols in this blockchain model of secure computation without explicitly stating this fact. For instance, this paper designed a secure lottery protocol over Bitcoin. I guess they don't have a formal security proof or security model. And then zero cash is another example. For instance, I'll mention more about zero cash's security model later. And there are also these very nice works by Bentov and Kumaranson, and also this one. And then these two papers have some degree of modeling, but the model is not exactly so general to cover programmable smart contracts. Okay, so it would actually be very handy to have a unified modeling framework to define security of protocols in this model, and to also for formally reasoning about the security of protocols in the blockchain model of secure computation. So that's what we do. And it turns out that there's also some non-trivial challenges that we encounter when doing the modeling. For instance, we realized that in order for the models to be usable, we'd like to have certain composition theorems that are actually not covered by UC, GUC, or GNU-C. So my student Andrew Miller is actually working on augmenting these models like UC, GUC, GNU-C to have the new composition theorems that we want. Okay. Okay. So I would like to talk about a cool system that we are building right now. The system is called Hawk. For example, in this picture, this is a hawk and this is a serpent. And as we all know, the Ethereum's programming language is called Serpent. So Hawk will provide privacy-preserving smart contracts. And let me motivate this. And as I do this, I will give you an example of a smart contract. So this is one of the canonical examples, an auction contract. In this auction contract, this contract will receive bids from parties. And whenever it receives a bid, it will check if the party indeed has this amount of money in its balance. And if so, it will deduct the bid from this party's balance. So effectively, at this point, the contract is withholding this amount of money on behalf of this party. Okay, and whenever, let's say there's an auctioneer, and whenever the auctioneer says close, to close the auction, and the contract will basically decide who is the highest bidder, and the bidder will be the winner, and he will pay the second highest price. Okay, and then the contract will basically update the ledger accordingly based on the result of the computation. Here, so this contract can easily be implemented on top of Ethereum. But there's one big problem. One of the big elephants in the room is privacy. So here, as we can see, the bids are visible to the public. And in something like a second price auction, what you really want is that the users should not be able to see each other's bids until they submit their own bids, because otherwise the auction can be subject to certain manipulations. Okay. So that's one example. And here is another interesting example. So this code snippet is resembles part of a contract that my undergraduate students wrote for a smart contract programming lab. Okay, and here the contract is very simple. The two players are playing rock, paper, scissors, and they each send their input choice to the contract, rock, paper, or scissors, and then the contract decides the winner and gives the bets to the winner. So this is the part of the contract where the parties are sending inputs. And of course, the problem here is that the inputs are visible to everyone. So if I'm smart, I'm going to wait for you to send your input and then decide what should be my own input. Okay. Okay. So it seems like with something like Ethereum, there isn't an easy way to achieve privacy on-chain, and all of your financial transactions will be exposed to the public. And also, the pseudonymity guarantees of these decentralized cryptocurrencies, they are simply not strong enough, because in many cases, for instance, in our sealed bid auction, it's not enough just to be pseudonymous. You also want to hide the details of the financial transaction, like how much money is being exchanged. And also maybe, for instance, in like financial swaps, privacy can also be very important. So in Hawk, we allow non-specialist programmers to write contracts. So to write contracts in Hawk, you don't have to be a cryptographer. Basically, we will compile your program into a privacy-preserving protocol that can run on top of a decentralized blockchain system. Okay. So let me kind of very quickly explain how the protocol works. I'll keep it very brief. So the idea is that in the beginning, the parties will commit their inputs and in this case, the values, we can think of the values as the parties' bids. So they commit these to the blockchain. And one thing to note is that the money commitment is not an ordinary commitment. It's like a cryptographically fancy commitment. Okay. Because there are some special constraints on money, like money needs to be conserved, money cannot be created, and therefore these commitments needs to be some cryptographically fancy commitment. Okay, and then in the second stage, it's called the compute stage. The parties will encrypt their inputs and value to the manager's public key. So essentially, the parties are opening their commitments to the manager. And they also attach a zero-knowledge proof to show that the computation is done correctly. okay, now the manager can see all of the parties' inputs and bids, and he can perform the computation on behalf of all the parties, and then he will compute, and these are kind of privacy-preserving coins, so he will compute these outputs, and then he will encrypt outputs to each party's public key. So this output I is necessary for party I to later spend this private coin. Okay, and then of course this manager will attach a zero-knowledge proof to show that all this computation is done correctly. Okay. So one thing that I want to mention is that this NIZK proves two main things. One is that the payout distribution is correctly computed from this contract program, and in this case, the contract program is our auction program. And secondly, this zero-knowledge proof needs to show that the money is conserved in the sense that all the input coins must equal to the sum of the input coins must be equal to the sum of the output coins. Okay, so in this sense, we can preserve the security of the currency because we don't want money to be created out of thin air and so on and so forth. Okay, so this is a very, very simplified version of our real protocol. It is important to note that this auctioneer is only minimally trusted in the sense that it is not trusted for correctness because every computation this manager or auctioneer does has NIZKs to vouch for its correctness. It is not trusted for input independence. And what do I mean by input independence? In the case of auction, it means that users should not see other users' bids before submitting their own bids. So even if the manager colludes with parties in the system, he cannot disclose bids to the other parties before all parties commit to their bids. And also importantly, the manager is not trusted for the security of the currency. Like for instance, the manager cannot create money out of thin air. And finally, so basically this manager is only trusted for posterior privacy and within the scope of this contract. Like if you have other contract instances running in your system, these other contract instances don't have to trust your manager. Okay. So the reason why we introduced this manager is mostly for efficiency because it's also easy to implement this manager just with generic MPC, but we didn't do that because this would not be very practical. It would actually be very attractive to implement this manager using something like SGX. Okay. So I'll leave it at that. And I'm going to quickly flash some of the contracts we have. SGX is Intel's new processor, and they have this SGX security extension, and basically you can think of it, so if you have heard about things like trusted computing, TPMs, SGX is supposed to provide similar security properties, but with stronger guarantees, and it's also much more efficient than something like TPMs and... Yeah, basically it will provide things like encryption, authentication of memory, attestation of the computation, and so on and so forth. Basically you can think of it as an ideal functionality in crypto, a crypto trusted third party. Okay. So this is just to flash some of the contracts we have composed with Hawk. This is sealed bid auction. Like rock, paper, scissors, Kickstarter, like a crowd fundraising, and financial swap. And this is a picture my student made for the compiler. I'm not going to explain it in detail, but it's a pretty picture. We have implemented a preliminary prototype. The performance numbers you see are not going to be the end performance numbers because there are a lot of optimizations that we wanted to make, but we haven't had time to make yet. So right now, with 100 users, if we implement 100-user auction or crowd fundraising, the auctioneer runs, the most expensive part is the snark proof, And the auctioneer takes about 2.7 minutes to run the snark proof, and each user takes about 50 seconds. And for the user's costs, it's actually independent of the number of users in the system. Okay. I'm going to say a few final words about Hawk and draw some relations to upcoming talks, and then I'm going to quickly end. One thing that I neglected to mention is that Hawk supports financial fairness in the sense that if parties abort from the protocol, they will be financially penalized, including the manager. I won't go into the details because actually Ranjit is going to give a talk on Wednesday about the topic of fairness. And I'd like to point out that their results can essentially be reformulated in our blockchain UC model, and these results can be restated. Okay, and the second thing, like I said, our protocol relies on zero-knowledge snarks. And one key insight is that on-chain computation is very expensive because on-chain computation is done by all miners, and in reality, you also have to pay transaction fees for the on-chain computation. And that's why snarks can be desirable for designing protocols in this blockchain model, in the sense that you can do snark verification on-chain, which is constant cost, and then you try to factor most of the computation away from the blockchain. I will leave it to Michael Wafish and Aaron Tromer to talk about snarks on Wednesday. Aaron is also going to talk about zero cash, which also builds on top of snarks. And I like to mention that Hawk is strictly more general than zero cash and is likely more secure. So when I say strictly more general, basically zero cash is a privacy-preserving cryptocurrency, but they only allow direct transfer of money between users. So you can roughly speaking think of zero cash as realizing the private version of the Bitcoin global ledger functionality. But that's not a precise statement. But whereas in Hawk, we support full programmability. So zero cash doesn't support any programmability. And zero cash has an indistinguishability-based security notion, and their security definition seems to not preclude certain leakages. Our protocols are proven secure under our blockchain model of secure computation. This doesn't mean that zero cash's protocol is necessarily insecure. It just means that there's no obvious way to prove their protocol secure under a desirable simulation-based security notion. Okay. I wanted to cover this, but it seems like I won't have time, so I would just make a very quick announcement. These smart contract systems can be used for good, but they can also be used by the bad guys to conduct crime. Okay, so basically Bitcoin has already stimulated a lot of crime activities, and the high-level message is that smart contract can make it worse. Okay, I won't have time to actually cover any of the details because I think
going over the time is a crime.
Yes, that's a crime too. But I would like just to quickly mention, like we have devised criminal contracts for things like document leakage, site defacement, assassination, and also key theft. It turns out that there needs to be some non-trivial techniques in designing these criminal smart contracts, and our paper basically talks about these techniques. And part of the
left as an exercise for the audience.
And this is not an encouragement for you to conduct crime, but rather we would like to raise awareness about how technology can potentially be misused. Okay. Yeah, it would be very interesting to think about how to basically deploy these technologies in a way that can help law enforcement to defend against such crime activities. Okay. So finally, I like to say cryptocurrency is very cool and deserves academic attention. And one thing that's really fascinating about cryptocurrency is that it brings together all these different disciplines. I talked about crypto. I touched just a little bit on programming languages, but then there are all these other things like economics, game theory, mechanism design, which I didn't have time to cover. So I strongly encourage you to go to Andrew Miller's talk on Thursday, and he will give an overview of the research perspectives and open research problems related to cryptocurrency. Finally, I'm excited to announce that we are actually establishing a new initiative and joined between Cornell Tech, and Berkeley. It's called IC3, Initiative on Cyber Currencies and Contracts. So this will basically help to foster collaborations between academic research and real-world financial institutions and startup companies. We have postdoc positions available in programming languages, crypto security, and distributed systems, anything that's related to cryptocurrency. Okay, thank you very much.